Greetings to all and welcome to this lecture. We are in module 6, lecture number 3, Simplified All Region Model part 2. In this lecture, we are going to see, can we formulate our ID with respect to charge instead of going for surface potential, and also we will see the formulation of the current in terms of quasi-Fermi potential. These are the learning outcome of this lecture, which helps you to understand the simplification in the modeling and how can we proceed for quasi-Fermi potential modeling. Let us do a quick recap. In the previous lecture, we have seen that we were getting the nonlinear term in terms of psi s as psi s to the power 1 by 2 or psi s to the power 3 by 2, and that nonlinear term was coming because of bulk charge, because we know that bulk charge is given as minus gamma Cox dash square root of psi s. If you take this bulk charge value as it is, you will get 1 by 2 power term, and if you integrate, you will get 3 by 2 power term. So instead of avoiding this non-linearity, we said that can we linearize the function around some extension point. So we choose the extension point as psi se in the previous mentioned graph between Cb dash over Cox dash and psi s. We said that by using a Taylor series expansion, we can linearize the system around this expansion point. We said that when you are going for linearization, this minus qb dash can be rewritten as Cox dash into gamma times of square root of psi se plus gamma by 2 times of square root of psi se into psi s minus psi se. In this sense, you actually ignored the non-linearity term. By putting this linearized qb dash term into qi dash, you have removed the non-linearity of surface potential on qi dash. So ultimately the qi dash equation came like this. Based on the choice of psi se, we defined two models as body reference model and source reference model. We said that if you are choosing as an expansion point of psi se, which is psi s naught plus psi sl divided by 2, then this will give you a body reference model, and when we will choose psi s e is equals to psi s naught, this will give you a source reference model. Accordingly, we found the linear equations in terms of psi sl minus psi s0 for IDS1 and IDS2. We also claim that the accuracy of this linearizing point depends upon what is the slope you are choosing. This slope is nothing but gamma divided by 2 times of root psi se. So based on the choice of linearizing point or expansion point, you are actually getting the accuracy in your linearization. In this lecture, we will see, can we formulate our drain current in terms of charge instead of using the surface potential. So if I am going to formulate the current equation in terms of charge, then I need to linearize this charge equation, because I know that the surface potential and the inversion charge are strongly non-linear. It means qi dash can be written as minus of 2 into q into Na into epsilon s into psi s plus phi t e to the power of psi s minus 2 phi f plus Vcb over phi t minus square root of psi s. So if you see this equation, where we will find the surface potential and the inversion charge are highly non-linear. So can we find out some linearization such that we can simplify our model? To move further, we will find the linearization between qi dash and surface potential. If you see the two terminal MOS structure, where we were applying VGB and we were saying that because of VGB there is a surface potential coming up, and this surface potential causes an inversion. So if we write a simple Q equals to CV equation, we can say Qi dash is equals to Cox dash into psi s. However, we know that VGB is not causing a direct drop of psi s, meaning if you write a potential balance equation, then there will be a drop across oxide and contacts. So we can simply say a fraction of VGB drops across inversion charge. We can simply use this formula to linearize our inversion charge equation. So here Qi dash can be written as alpha times Cox dash into psi s. Using this technique to linearize Qi dash with respect to psi s, we can find delta Qi dash by delta psi s is equals to alpha times of Cox dash, right? And now we'll rewrite our current equation, which was given by W by L into mu into Qi0 to Qil minus Qi dash. This was psi s0 to psi sl minus Qi dash into d psi s. So we'll replace this d psi s from here as dqi dash by alpha into Cox dash, and we'll change the limits of this integration as Qi dash to Qil. By doing so, we'll actually form a current equation which is not dependent on surface potential, and we'll get the whole equation in terms of inversion charge. If you simplify this, you will get Qi dash by 2 whole square as an integration, and you put the limits as Qi dash 0 and Qi dash L. Take alpha into Cx common, you will get mu into W divided by L into Cox dash, and you take this 2 also out. So ultimately you will get W by L mu divided by 2 into alpha into Cox dash into Q dash I 0 square minus Q dash I L square, where this is the charge, this is the inversion charge near the source channel junction, and this is the inversion charge near the channel drain junction. Similarly, if you rewrite the equation of IDS2, which was IDS2 is can be written as W divided by L mu into phi t into Qi L dash minus Qi 0 dash, right? If we see carefully the current IDS1 and IDS2, then they are function of Qi dash and Qil only. There is no function of surface potential coming into picture. That is what it is called simplified formulation of all reason model using inversion charge. So let's linearize this model further, because we do have some non-linear term. So how can we linearize this? For that, in general, we choose a linearization point as psi sa, because we need to choose some surface potential around which we need to get the inversion charge, and then that inversion charge value we will put back into the equation to get a closed form equation in terms of inversion charge. So ultimately the goal is we are going to develop a equation of current which is only a function of inversion charge, but ultimately the inversion charge is a function of psi s. So we need to linearize this function around some point. For the sake of simplicity, we are choosing that psi sa is a linearization point, right? If we are choosing psi sa as a linearization point, we can simply write alpha is nothing but 1 plus gamma divided by 2 times of root psi se, where psi se was expansion point, what we discussed in previous lecture. For the sake of simplicity, as I mentioned, that we are taking psi sa as a linearization point. So this can be 1 plus 2 times of root psi sa. If you remember our module 2 and module 3, there we have discussed that this is nothing but n, where n is the slope factor which defines how my surface potential and the gate voltages are related. So this was the definition of N when we said that when we plot the surface potential with respect to Vg, we will get this kind of characteristic. We said that in weak inversion and depletion, ultimately the surface potential is linearly dependent on VGB. Overall, this N factor tells us what is the control of gate over your channel, or you can say how much good control do you have over the channel of your external gate to body voltage. In that condition, in previous lectures we derived the formula for N, which is nothing but 1 plus gamma divided by 2 times of root psi SA. So here alpha can be replaced as the known factor, which is N, and we can use this N factor in general our current equations. This type of model is often called inversion charge based model or charge controlled model, or in simple or in general unified charge controlled model or UCCM. How can we solve this kind of model? Ultimately, you take a value of psi s, put that value of psi s in this equation, calculate for psi s, and how can we solve this model? Ultimately, you take this equation, solve for psi s, because Qi dash is nothing but a function of psi s. You solve for psi s and then put that value of psi s into your inversion equation, and hence you will get a closed form equation which will give you the drain current equation, only dependent on inversion charge. How can we further linearize this system of Qi dash? As we mentioned that when we need to linearize, then we need to choose a linearization point. So in this case we are choosing that expansion point is nothing but psi SA. So can I use Taylor series expansion to further linearize this Qi dash, which is a function of psi s, so around this point. So Qi dash for psi SA plus dQi dash per d psi s at psi s equals to psi SA into psi s minus psi SA plus higher order terms. We will ignore the higher order terms and we will see how we can use this linearization to simplify our model. This will give you 0, meaning when the surface potential reaches the value of psi SA, you will go in depletion or weak inversion, and in weak inversion and depletion we assume that the inversion charge approaches to 0. So this kind of linearization helps us to use some of the approximation what we followed earlier. That is what Qi dash of psi s, which is a nonlinear function of psi s, can be rewritten as 0 plus dQi dash by d psi s at psi s is equals to psi SA into psi s minus psi SA. Now what is this? We have seen in previous slide that dQi dash by d psi s is nothing but alpha into Cox dash. So dQi dash by d psi s is nothing but alpha into Cox dash. We need to calculate this value at psi s is equals to psi SA. We have also discussed that alpha is nothing but n when you are keeping psi s is equals to psi SA, or the expansion point is chosen as psi SA. So this alpha is now converted into n. So ultimately the expansion or linearization of Qi dash can be written as Qi dash is equals to n times Cox times psi s minus psi SA. Now let us see how we can simplify this equation and solve for linearization. Here this is a well known equation we have derived earlier, which says that my inversion charge is non-linearly related with the surface potential. So let us do some simplification. 2 into q into Na into epsilon s, take root psi s common, you will get 1 plus phi t by psi s e to the power of psi s minus 2 phi f plus Vcb over phi t to the power 1 by 2 minus 1. I have just taken psi s from this and this side common. If you do so, you will get 1 plus x to the power 1 by 2. This can be expanded as 1 plus x by 2 plus higher order terms, considered that x is small. So you can ignore the higher order term and you can rewrite this equation as 1 plus phi t divided by 2 times of psi s e to the power of psi s minus 2 phi f plus Vcb over phi t minus 1. So this plus 1 and minus 1 get cancelled, and ultimately you will get a equation which relates the inversion charge and the surface potential linearly as minus of 2 into q into Na into epsilon s into root psi s, in bracket you will get phi t divided by psi s into e to the power of psi s minus 2 phi f plus Vcb divided by phi t. Correct? If you solve further, you will get this term can be written as square root of 2 into q into Na into epsilon s divided by Cox dash can be written as gamma. So this term can be written as gamma into Cox dash with a negative sign, multiply this inside, and there will be a 2 terms coming into picture. We missed the 2, so here 2 will be there, and minus gamma into Cox dash into phi t divided by 2 times of root psi s into exponential of psi s minus 2 phi f plus Vcb over phi t. This is nothing but qi dash. Now if you rearrange the term, you will get minus qi dash divided by Cox dash into phi t, and this gamma by 2 times of square root of psi s can be written as n, because n is nothing but 1 plus gamma divided by 2 into square root of psi s, where n is approximately written as gamma divided by 2 times of root psi s a, where this is an expansion point, so we need to write psi s a. Correct? So this can be written as n into e to the power psi s minus 2 phi f plus Vcb by phi t. Now again you take n this side and take log at both sides. So ultimately you will get log of minus qi dash divided by n into phi t into Cox dash is equals to psi s minus 2 phi f plus Vcb divided by phi t. Now again I wish to remove the term of psi s in terms of qi dash. So I can go back in this equation where we just linearize qi dash and psi s. So we will get qi dash divided by n into Cox dash plus psi s a is equals to psi s, and I will put this psi s value here to get a simple form of qi dash only. So this is phi t Cox dash is equals to this psi s is nothing but psi s a minus 2 phi f plus VCB over phi t, and you will get another term Qi dash by n into Cox dash into phi t. You take this term at this side and ultimately you will left with this term plus this term is equals to psi s a minus 2 phi f plus VCB over phi t. Now you remember we have defined a pinch off voltage. We said that when you increase the VCB, then there will be a surface potential point, there will be a point where the surface potential attained a value of psi SA, correct? That is defined as pinch off voltage. So we will just replace that pinch off voltage definition here, and ultimately we will get this simplified form which relates the inversion charge with respect to VCB. We will incorporate this inversion charge expression in our drain current expression, and we can find out the drain current expression only in terms of inversion charge. Now let us define some components which is forward and reverse bias. We have seen that IDS1 now can be defined as this, which is having only inversion charge, there is no component of surface potential. Similarly, IDS2 can be defined as this. Let us simplify it further and find out the separate terms of Qi dash 0, which is nothing but the charge near the source channel junction, and Qi dash L, which is nothing but the inversion charge present at the drain channel junction. So let us rewrite this equation as W by L mu into Qi dash 0 divided by 2 into alpha into Cox dash minus phi t into Qi dash 0. So this part is only a function of Qi dash 0. It means the left hand side is the function of only inversion charge which is present near the source channel junction, and the right hand side is only dependent on the inversion charge which is present at the channel drain junction. So this component is called it as forward component, and this component is called as reversed component. So we define the drain current comprises two components, one is forward component and one is reverse component. The forward component is a function of inversion charge at source channel junction, and the reverse component is a function of the charge or the inversion charge present at channel drain junction. Now let us consider you have applied VGB and there is sufficient amount of Qi dash and Qi L is available. If VDB and VSB are same, it means what? The inversion charge is purely dependent upon VGB, meaning the value here and the value here is same. So if you find this value and this value is exactly equal, then ultimately IF is equals to IR. Let me make you clear. Suppose you are applying VDB exactly equals to VSB and you are applying a gate voltage. Let us say the gate voltage which makes the channel inverted. So in the channel the inversion charge is present between 0 to L. In that condition Qi dash 0 is exactly equal to Qi L dash. If you keep this equal, you will get IF is equals to IR. In that condition, the drain current is equals to 0 if IF is equals to IR, which makes sense also because you are not applying a potential in the horizontal direction and hence there is no flow of carriers. Now assume you are increasing VDB. If you increase VDB, the surface potential here will increase. Because of increase in surface potential, the region of operation enters from strong inversion to moderate inversion to weak and to depletion, and hence the charge here QIL dash approaches to 0 when you increase the VDB. If you increase VDB in such a way that QIL approaches to 0, then you will find the reverse component will be 0, and hence the current will be only carried by a forward component, which is nothing but a saturation current. Similarly, if you increase VSB keeping VDB as constant, then what will happen? The inversion charge at source channel junction will approaching 0. If that is the case, then there will be a reverse saturation, and hence the current will be reverse. That is what IF component goes to 0. So there will be a reverse component, which we discussed when we were discussing about the symmetry of the MOSFET. Let's move further and analyze our model based on quasi-Fermi potential. In our previous analysis, we have assumed that the inversion layer is having infinitesimal thickness, meaning we considered charge sheet approximation, and based on these approximation we derived our previous models, and we simplified the model as source reference or body reference model. Now let us consider that you do have an inversion charge which flows in the y direction as well. So let us consider you do have a MOSFET, and this is x direction, means from source to drain is plotted in x direction, whereas this direction is y. In charge sheet approximation, we consider that the thickness of the inversion region is very small in y direction, and they forms a sheet of the electrons in NMOS. Whereas let us consider the electrons are moving in vertical direction also. So for sake of simplicity, we are assuming that the vertical direction is divided into very small strips of delta y. In each strip, the electron concentration will be different. However, we are ensuring that the electron will flow from source to drain and a laminar flow is maintained, meaning if we see a particular strip, then the electron will flow in this horizontal direction, which gives rise to a current. So ultimately, if we are interested to calculate the total current, we need to integrate the charge between these points. Between a point deep in the surface, we generally assumed YC, and this is Y surface, what we have discussed in module number 2. So let us see how we can analyze in terms of quasi-Fermi potential or in terms of applied VCB voltage. So at any point of x and y, the current can be given as the drift component and the diffusion component, but here it is interestingly to note that the current is not only a function of x, but the function of x and y. It means the electron can go inside to the body as well, or it can go vertically also. So the drift component can be given by W into dy into Q into mu into Nx d psi by dx. Again, to give you clarity, we have discussed this drift part earlier in module number 1, where we said that suppose we do have a cuboid with dimensions b, a, and the height is c, then the current can be given as q by tau, where tau is a transit time and tau was given by the total time traveled to this distance a by Vd, and the total charge was given as n into q into volume. So a can be cancelled and you can write n into q into b into c into Vd. Vd can be written as mobility into electric field. So electric field can be written as d psi by dx. Here b is nothing but the width of the MOSFET. So we are replacing b by w. C is nothing but the thickness. So if we are talking about one particular slice having a thickness of delta y, then we can rewrite as dy. N is the total number of electron concentration in that particular slice. Mu is the mobility with which the electron flows in that slice. Q is the electronic charge, and this is a potential. Interestingly to note as the electrons are moving in x direction as well as y direction, the potential is a function of x and y both. But we are actually calculating what is the electric field in x direction, which causes a laminar flow from source to drain. Similarly, the diffusion current can be written as minus W into dy into Q into mu into phi t, which is nothing but a diffusion constant replaced using Einstein equation, and this is dN by dx, where n can flow in x direction as well as y direction. We can also express this nxy in terms of this. You remember when we were talking about 3-terminal structure, then we said that when you apply a voltage VCB, at that moment the electron concentration at the surface can be given by n naught e to the power of psi s, or psi as a function of xy minus VCB as a function of x by phi t. Here it is interesting to see that we are actually varying the terminal voltage, whether it is VDB or VSB, along x. So that is what this will be only a function of x, whereas the surface potential, which is responsible for causing a inversion charge in this direction and also causing a flow of carrier in this direction, that is what this will be the function of x and y both. So we will find delta nx by delta x as follows: n naught e to the power of psi xy minus VCB x by phi t. So this can be written as n naught e to the power of psi s x y minus VCB, it's a function of x only, phi t, and there will be a phi t terms comes in, and you need to do a differentiation by parts. So ultimately d psi s only psi by dx, better it's a partial differentiation because now the potential is a function of x and y, but VCB is only function of x. So we can rewrite this as, here this term is nothing but nxy. That is what you are getting this expression when you are differentiating the nxy with respect to x. Now you put this function in the diffusion current equation. Ultimately you will get this equation, because in diffusion current equation we do have an expression of delta n by delta x. When you put that equation, you will get this equation. And to find out the total current, we need to add the drift component and the diffusion component. So when you add, you will find that this term is getting cancelled. You see, we do have a term of dou by dou x psi of xy in drift part. Similarly, we do have a term dou by dou x of psi s in diffusion part. So this will get cancelled, and ultimately you will get a equation which is a function of VCB, and the VCB is a function of x, right? Now to find out the closed form equation of current, we can integrate the charge, which is nothing but nxy, between the mentioned limit as I have discussed here. Like, let us consider a point yc which is deep in bulk and y surface. So if I am interested in the total charge, I need to integrate or add all the slices. So I am integrating from some point to y surface. That will give me the total charge. So ultimately we need to integrate to get the total inversion charge, which can move in the x direction and can also move in the y direction. So in general, we can rewrite the IDS equation as mu into W into minus of Qi dash dVCB divided by dx. And when we were discussing about 3-terminal structure, we said that this VCB is actually causing a Fermi level split that we call as quasi Fermi level, because this is modulating the inversion charge, and we have found that the inversion charge or the electron contribution is actually given by n naught minus of Vcb divided by phi t when we were discussing about 3-terminal structure. So to further simplify, we'll integrate this equation from 0 to L. That will give us the total current equation as W by L mu into integration of inversion charge with respect to Vcb, and we know the value of Vcb is Vsb at the source side and Vdb is at the drain side. So if you integrate this equation, ultimately you will get a closed form equation in terms of Vcb. So if you integrate this equation, you will get a closed form of drain current equation. This equation can further be explained by plotting Qi dash versus Vcb. This is what we have explained in previous lecture when we were plotting minus Qi dash with respect to psi s. So ultimately when you increase Vdb, then the area is increasing and hence the current is linearly increasing, but at a certain point what will happen, this inversion charge approaches 0 and hence you will get a saturated current. To be very clear, such kind of interpretation is not possible in moderate and weak inversion. Let me summarize. In this lecture, we have derived a closed form equation of drain current in terms of only inversion charge. We said that instead of going for deriving in terms of surface potential, much more accuracy can be attained when we are deriving the equation in terms of inversion charge. Further, we have seen that the drain current model can be derived using quasi Fermi potential. So we'll stop here for today. Until then, take care.